Hey everybody, welcome to Algo Expert. In this video, we're going to be covering the selection sort algorithm. This isn't the most performant of sorting algorithms, but it is pretty easy to understand and simple to implement. So let's dive into it. How does it work? Well, basically you're given a list of numbers, right? Here we've got 8, 5, 2, 9, 5, 6, 3. And the way we're going to sort this list of numbers is by dividing it into two sort of separate lists within that list. We're not going to be creating new arrays, but within this list, we're going to have one sublist that represents unsorted numbers and one sublist that represents sorted numbers. And so at the beginning, we start with our entire list representing that unsorted list. So I'm going to underline the entire array in purple to show that all of these numbers right now are not sorted. And what we're going to do is we're going to iterate through this unsorted list a bunch of times, and each time we're going to find the smallest number in that unsorted list. Once we have the smallest number, we're going to append it to the sorted sublist, which will basically we'll make room for it here at the beginning of the array. And we're going to keep doing that until we no longer have an unsorted sublist and we only have a sorted sublist, which is going to be our entire array. And this is all going to happen in place in the array, the input array. So let's start. We start with an arrow above our first number, 8. And this arrow kind of represents the index of the smallest number. Where does the smallest number in our unsorted list where is it positioned? And so here we start with 8. And now we start traversing the array to find perhaps a smaller number. So we move on to this 5. Is 5 smaller than 8? Yes, it is. So we can move this arrow above the 5. Then we get to 2. Is 2 smaller than 5? Yes, it is. So we can move this arrow to the 2, meaning the 2 is our smallest number currently. Then we move on to 9, not smaller than 2. We move on to 5. 5 is not smaller than 2. Move on to 6, move on to 3. Neither of those are smaller than 2. So 2 is the smallest number in our current unsorted list. So we can swap the 2 with the 8 because we want to make our sorted list here at the beginning of our array. So we're going to erase this 8. Erase the 2. We can put the 8 here, and we can write the 2 at the beginning. And I'll put it in green so that you can really tell this 2 is in the sorted sublist and is in its final position. So now we can even erase here part of the line and underline the 2 to show this is the sorted sublist, and this here is the unsorted sublist. So now we move the arrow back to the beginning of the unsorted sublist, and we find the new smallest number in that sublist. So 5 is our current smallest number. Start traversing the unsorted sublist. Get to this 8. Is 8 smaller than 5? No, it's not. Is 9 smaller than 5? No, it's not. Is 5 smaller than 5? No, it's not. They're equal to each other, so we don't need to do anything here. Is 6 smaller than 5? No. What about 3? Yes, 3 is smaller than 5, so we can move the arrow above the 3. And now we're done. We no longer have numbers in this unsorted list, so we want to append this 3 to our sorted sublist that only has a 2 right now. How do we append it to the 2? We just swap it with the first number in our unsorted list. So we erase this 5. Let's erase it here. Erase the 3. And put 5 at the end. And 3 in sorted order here. And we can erase part of that line and extend it in green here. All right, now we want to find the smallest number in our new unsorted sublist. So we start at 8, move on to 9. Is 9 less than 8? No, it's not. Is 5 less than 8? Yes, it is. So we can move the arrow above the 5. Is 6 less than 5? No. Is 5 less than 5? No. So 5 is our smallest number. We can swap it with the 8 to append it to the sorted sublist. So we're going to put 5 here, and we're going to put 8 here. We can extend the line. So now our sorted sublist has 2, 3, and 5. So you really see, we're literally applying the functionality of the algorithm that I described at the beginning of the video, which was find the smallest number in this sort of sublist of unsorted numbers and append it to the end of the list or sublist of sorted numbers. So now we're about halfway done. We have 9 as our smallest number. Is 8 less than 9? Yes, it is. So we can move on the arrow. And now we can see that we'll be able to move the arrow to the 6 and then to the 5. Because 6 is less than 8 and then 5 is less than 6. So now we swap 5 with 9. So let's erase 9, erase 5. We can put the 5 here. And we can put the 9 here. So erase this line, extend the sorted line. Now we can move the arrow above the 8. 8 is our current smallest number. Is 6 less than 8? Yes, it is. So we can move the arrow above the 6. Is 9 less than 6? No, it's not. So 6 is our smallest number. We can swap 8 and 6. 6 and 8. All right. Erase part of that line and extend this. So now you can start to see that our sorted list is really getting big, whereas our unsorted list is very small. And we're at the final iteration here. We're going to have 8 as our current smallest number. Then compare 9 to 8. 9 is not smaller than 8. So 8 is our smallest number. And we can just keep the 8 in its position. We'll write it in green. Extend the line here. And now, since we are at the last number in the array 9, we know 9 must be in its sorted position. So we're done. We can erase everything and just put 9 there. All right. So our entire array is in sorted order now. We did this all in place in the same input array that was given to us. So this naturally means that the space complexity is going to be O of 1 space. All we did was swap numbers within an array. And the time complexity is going to be O of n squared, where n is the length of our input array. Why is it O of n squared? Well, because you saw that we kept reiterating through parts through that unsorted sublist, which kept having a length reduced by 1 at every iteration. But so that should kind of tell you, oh yeah, we're likely going to be using 2 for loops or a while loop and a for loop, and that all points to O of n squared. So the time complexity of selection sort is going to be O of n squared time. Not the best, right? Not the most performance sorting algorithm. It definitely is not as good as quick sort or heap sort or merge sort, but it is really simple to implement and very easy to understand, so it's not that bad. I hope this conceptual overview was helpful. I hope that you were able to understand what selection sort is and how it works. Let's implement it in code now. All right, so we've got our selection sort function defined, and it takes in an array of integers. So what do we want to do? How do we implement this in code? Well, remember that we want to divide our array into 2 sublists of sorted numbers and unsorted numbers. And how are we going to represent these sublists? Well, we're basically going to keep track of the index of the first number in the unsorted sublist. And at the very beginning, all of our numbers are unsorted. They're all in the unsorted sublist. So our current index is going to be equal to 0. This current index, as I just said, is going to be the index of the first number in the unsorted sublist. And then what we're going to say is we're going to say while current index less than len of array minus 1, do stuff, right? Why are we bringing our current index all the way to len of array minus 1, which is the final index in our entire array? Well, that's saying when our current index, which represents the index of the first number in the unsorted list, gets all the way to the final index, that means that our unsorted sublist is only going to have one number, and that means that we're done, right? That last number is going to be in its final position, and our entire array is going to be sorted at that point. So all we have to do is do stuff while our current index is less than len of array minus 1. And so here, what do we want to do? Well, we want to find the smallest number in our unsorted sublist. Or rather, we want to find the index at which the smallest number in our unsorted sublist is located. So we can say smallest index is going to start at current index. We initialize the smallest index to be the current index, which is the first number in the unsorted sublist. And then that's when we can do a for loop. We can say for I in range current index plus 1 all the way to len of array. If array smallest index is greater than array of I, then smallest index is going to be equal to I. So what are we doing here? We're iterating through the unsorted sublist, starting at current index plus 1, the second number in the unsorted sublist, going all the way to the end of the array. And at each point, we're saying if the number that we have, which is located at smallest index, which we initialized to be current index, if this number, which is our potential smallest number, is greater than the current number, then update the smallest index to be the current index. And that's it for the for loop. That's how we find the smallest number. And once we have our smallest number, we can just go ahead and swap. We'll write a helper function, a swap function, but we can go ahead and swap the current index, or the number of the current index, and the number of the current smallest index. So our swap function, if we define it now, it's going to take one index, a second index, and then our array, and we're just going to say array of I, array of j equals to array of j, array of I. Now, if you were writing this in JavaScript or in another language, this might be a bit more involved. You might have to write like 3 lines and have a temporary variable. But here in Python, you can just make this a one-liner. I still like abstracting out the swap function, just because I think it makes the code a little bit cleaner. Anyway, once we've swapped the smallest number with the current IDX, by the way, why are we doing this? Remember, the current IDX represents the starting position of the unsorted sublist, and that's where we want to do the swap. That's essentially going to append the smallest number, which is located at smallest IDX, to the end of our sorted list. And then once we've done that, we just want to increase our current IDX by 1, because now our unsorted sublist no longer starts at current IDX, it starts at current IDX plus 1. And then at the end, we can just return the array. And we're done. That is selection sort. We can put the time complexity to be O of n squared time, and the space complexity is going to be O of 1 space, as we explained in the conceptual overview. So I hope this was helpful. I hope this was informative. I hope that now you understand how selection sort works. If you ever have to implement a sorting algorithm and you don't really care about performance, this is a pretty simple one to implement. And I'll see you in the next video.